guys, welcome back to another video. In this video we are going to solve two exercises in classical mechanics, and in particular the exercises are about projectile motion, so basically the parabolic motion. In this first exercise, as you can read, we have a ball which is thrown horizontally from a height of 12 meters, and the velocity of the ball as it falls to the ground is twice compared to the initial velocity, and we have to find the initial velocity. So here we have already a little sketch of the situation. So the ball initially is here, and it is thrown from a height of 12 meters. So this is our 12 meters. So initially the velocity is purely horizontal, so it means that for t equal to 0, so 0 is the initial time, the velocity v at time t equal to 0 is completely horizontal, so it means that we have also just the x component at time 0. So initially we have just the x component, the horizontal component for the velocity, and then as you can imagine, the ball basically reaches the ground following a parabolic path. So the path is more or less this, a parabola, and at the end, so the ball will be here, and at the end, so as it touches the ground, the velocity is this one, so it will be the velocity v at time, let's say t star. Okay, so t star consists of the flight time, always the same, because at in every moment here along the path the ball goes down, obviously because of the gravity. So at every point we have the gravity here that pushes downwards the ball, and but the gravity obviously acts on the vertical direction, but as far as the horizontal direction is concerned, we do not have any force. So that means that if initially the ball is characterized by a velocity which we called Vx, or maybe we can call it Vx 0, this velocity is the same in the horizontal direction in every moment. So it means that even in the for the star, so when the ball reaches the ground, the horizontal component, so this component will be Vx0, so the same velocity that we had initially. So this means that this will be Vx0 squared, and then we have that the velocity in the y direction changes, because here we have a acceleration. So since the problem tells us that the final velocity is twice the initial velocity, it means that this term, so v studied at t star, will be 2 times this velocity. So this means that this will be 2 times Vx0 all squared. Okay, so this is the result that we get from the data, and this means that if we compute, we get 4 Vx0 squared, Vx0 squared plus Vy squared studied at t star. Okay, so this means that 3 Vx0 squared is Vy squared, and from here we get that Vx0 is Vy at t star over 3 under square root. Okay, so this is basically our result. Okay, let me move a little bit, and this basically means that now we have to find the final velocity in the vertical direction, so the velocity at this point for the y direction. But since in the y direction the ball is accelerated due to the gravitational force, we can write that since we know that initially the ball is here at a height of 12 meters, we basically can write that y at time 0, so y at time t equal to 0. No, actually we have to study y at for t equal to t star, and this is y0, which is 12 meters as we said, but we have to consider the height for t star, which will obviously be 0, because here if we take the origin So this means that we can write that y at t star, so the final height will be y0 plus y0 let's call it v y0 times t star. So this is the velocity in the vertical direction at time 0, so the initial velocity. And then we have minus 1/2 g, so the acceleration t star squared. So this is the equation of motion for the y direction, basically. But and we have to find the velocity at time t star. So here this relation is useful to find the flight time, because here the only thing that we do not know is t star, because the initial velocity for y is 0. So we get that t star will be t star will be 2 times y0 over g, all under square root. Okay, so this should work, yes, because this is this will be second, okay. And now to find the velocity, the y velocity, the final y velocity, we have to consider the equation for the y direction, which will be this one for the velocity. Minus g times t, okay. So this basically comes from the definition of acceleration, and we know that the initial velocity is 0, and we have to find yt star. So this will be minus g t star. So we get here minus because g is actually downwards, but we are interested in the module of this, in the absolute value of this quantity. So we can just consider the absolute value of this thing. So we can write plus in this formula. So this means that here if t star is this one and the velocity is g t star, the initial velocity will be so it will be g times 2 y0 over g under square root under and over 3 under square root. So this basically means that this will be we can write it also in this way, to y0 g over 3 under square root. Okay, and this should work because y0 is meters, g is meter over second squared, but all this is under square root, so we get a velocity. Okay, if you plug in at this point the values that we are given, you should get that the initial velocity is 8.85 meters per second. So more or less this should be the final result. Okay. second exercise, we have again a ball which is again thrown toward a wall at a distance d, and d is 7 meters, and the ball hits the wall at a height of h, and the height is 3 meters after a time of t. So we can again call actually this d star 1.25 seconds, and we have to find the velocity and the angle of throw. So this velocity, it is so we have to basically find the initial velocity and the angle of throw. So here again we can sketch briefly our exercise. So we have the ball, which initially is here on the ground, and we have a wall at a distance d, which is 7 meters, and the ball is thrown. So again it follows a parabolic path, so it is again a projectile motion, which will be something like that, more or less, and this height is h 3 meters. Okay, more or less. And we have to we know that the time of flight d star is 1.25 seconds, and we have to find the initial velocity. So initially we have a velocity which will be something like that. The vector velocity is obviously tangent to the parabolic path, and this vector forms an angle which we can call it theta. So the angle theta is the second thing that we have to find, and so we can call the initial velocity v0, and we have to find its module. So v0 module absolute value, and then we have to find theta. Okay. So in order to solve this exercise, again we have to resort to the equations regarding the motion of the ball in the x and in the y, along the x and along the y direction. So this means that for example in the x direction, which is always the easier, we have that x at time, so the horizontal space at time d star is 7 meters, which is d again, and we know that so d will be the initial velocity, so we can call it again for x0, because this velocity along the x direction will always be the same, times d star. Okay, so from here we can find the initial velocity as far as the x direction is concerned, because the initial velocity along the x direction will be distance over time, which is 7 meters over 1.25 seconds. Here, if you plug in the data, you will second. Okay, so this is the initial velocity as far as the x direction is concerned. So let's keep in mind that the initial velocity, so v0, is a vector of this kind, and again we can split this vector along the x direction, so we get vx0 as we said, and then we have to find also vy0, so the initial velocity in the vertical direction. And to find this, so to find the initial velocity along y, we know that the velocity along y as a function of time is given by the initial velocity along y minus g times t. Okay, so again we have minus because the gravity is pulling downwards. Okay, so in particular, if we consider t star, we get the velocity here, which will be minus g t star. Okay, so if we consider this equation, we actually we are unable to find the initial velocity because we do not know the final velocity, but we can resort to the other equation regarding the motion in the y direction. So we have to consider the space with respect to time. So we can write that y with respect to time is y0 plus this, so the initial velocity along the y direction times t minus 1/2 g t squared, as we saw in the first exercise. So again, if we consider the origin here, we get that the initial height will be 0, so this term is 0, and then we get that if we calculate the y, so the height for t star, this is 3 meters, because it is the height at which the ball hits the wall. So we have y t star, which is actually h, we can call it h, equal to the initial velocity times t star minus 1/2 g t star squared. So in this equation, the only quantity that we do not know is the initial velocity. So from here we have that vy0 will be h plus g t star squared over 2 over t star. Okay, and this should be correct because here as a numerator we have meters and then we have time here, so okay, we get a velocity. Okay, so we have to plug in our values. So h was 3 meters, and then we have 9.81 times 1.25 squared over 2, and then we have again over 1.25 seconds. Okay, if you get a calculator, you should get 8.53 meters per second, and this is the velocity, the initial velocity in the y direction. So at this point we can write that the initial velocity squared, as we saw previously, will be the initial velocity over x squared plus the initial initial velocity along the y action squared. Okay, so at this point we can plug in the values, and if you plug in the values you will get that the initial velocity is more or less 10.2 meters per second. Okay, so this is the final result. And as far as the angle is concerned, again we have that V0 forms this angle with the ground, but this angle is actually given if we calculate the tangent of theta with Vy0 and Vx0. So I'm basically saying that the tangent of theta is Vy0 over Vx0, and this means that theta will be tangent to the -1. And again, if you plug in the values here, you will get that theta is more or less 56